Alright, so this is the last section for, or last little topic here for mechanics that we're going to do here, or at least linear mechanics. And this one's about momentum. That's an M, momentum, and impulse. So let's go ahead and get started with that. Let's first define what momentum is. Well, momentum is essentially what Newton thought energy was. So momentum, and it's going to be a lowercase p is our variable to represent it. It is a vector, and it equals m times v. Okay? So it's a vector quantity, it's a lowercase p. There was a reason why it was this lowercase p. It had something to do with the word for momentum in a different language, but it's just p equals mv. The units for this are going to be pretty obvious. There's no special name for it. It's not like a Newton or a joule or something like that. It's simply a kilogram meter per second squared. So kilogram meter per second. I think I said second squared, but it's kilogram meter per second. And the wonderful thing about this is it's always a conserved quantity. It's always conserved. It's a vector, so you can conserve it in the x direction and in the y direction, but it is always conserved. So that's pretty much it for momentum. You just have to be careful. Essentially, the always conserved, like always. In a closed system, always conserved, you consider all of the objects that are interacting. This momentum is always conserved. So change in change in net momentum has to equal 0, or just net momentum initial has to equal net momentum final. So add up all the momentums of all your objects interacting initially, it'll equal all the momentums of all your objects at the end. This is regardless of there being like conservative forces or things like that. If there's friction involved, you're simply transferring the momentum. Like say there's friction on the ground, you're actually really just transferring the momentum into the ground, into the planet. So momentum is always conserved. It's not like energy where we can have heat loss that reduces momentum. That doesn't happen. This is locally conserved all the time. So then what is impulse? Well, impulse is just a special name given to the change in momentum. And sometimes, I don't often use this, but it can be represented by a capital J. It is a vector, but it's just change in momentum. Also a vector. If you're a Star Trek fan, you may have watched in like Star Trek Next Generation where they say go to impulse engines, where essentially you don't have to keep the engines running to keep yourself moving. You simply just simply give a little burst, change your momentum, and then you coast from there on. But it's just a change in momentum. So some places you'll go, you'll see they'll write a J for it, a capital J. Other places they won't do anything but just write delta P for impulse every time. I tend to be more in that camp that just writes delta P. So let's take a look at something here real quick. Let's take a look back at Newton's second law, F equals m times a. Again, vectors and vectors, but a is simply, by definition, change in velocity over change in time, right? Well, change in velocity times m, if we combine those two together, that's m times delta v. Well, that's going to be this, right? Assuming the mass doesn't change, right? This would be, assuming a constant mass, this is m delta v is what this becomes, right? Then m delta v is simply the impulse, change in momentum over time, is our force. So if we want to look at force, we can look at force in terms of momentum. And if we wanted to go one little step further here, you can do then that impulse equals force times time. Pretty good equation right there to use. So we've got that for impulse, we've got this for momentum, and then we just, of course, here just defined what is momentum. That's just going to be what? P final minus P initial, right? That's always changing. But we have a nice little equation here involving force for calculating the impulse. That being said, if you actually go and then looking at this force times time, if you do a graph of force as a function of time, right? Force as a function of time, then what you will get, you'll have some crazy graph or something, right? Well, what you end up with is if you take the area underneath this curve, right? If you take and look at it, when you do area underneath it, you're doing the vertical axis times the horizontal axis, because you're basically coming in here and you're drawing a tiny little rectangle here, right? A little rectangle column, and you're finding the area of it, and it's the force, the height times the width time, and then you're doing the next little rectangle here and doing the next little rectangle, and you're doing an area of all these rectangles, and they're all force times time. So this area underneath the curve, this area here, right, area under is going to be equal to the impulse, delta P. Okay, so this area equals impulse. All right, so area under curves, kind of keep that in mind. But remember, anytime you're given one of these graphs, you always want to check what's the slope and what's the area under. What are the dimensions going to give you? What kind of information would you get from this? Okay, so next thing we can do to kind of finish our little introduction to impulse and momentum is relate these back to kinetic energy. Now, originally, I think that Newton thought this was that momentum was the kinetic energy of an object, but ultimately Émile de Châtelet showed that he was wrong, that the kinetic energy was actually based on the velocity squared, so mv couldn't be it anymore, and so we can do a kind of a kinetic energy versus momentum. And some of the things we know: kinetic energy, scalar, vector, right? So this has no like physical direction like that, but here this one does. So this is a vector, this was a scalar, and then we can actually rate them. This was the kinetic energy equaled 1/2 mv squared. Over here, momentum vector equals mv. But you notice these two kind of equations are pretty close to each other, and we can actually relate them to each other. So let's take kinetic energy equals 1/2 mv squared, and what I want to do here is I'm going to multiply this by m over m. Okay, and what that'll give me is an m squared v squared over 2m, which is mv squared over 2m, and mv is momentum. So we can write kinetic energy now. Nice little equation for us here. Kinetic energy is simply p squared, momentum squared, over 2m. So there's another little relationship between kinetic energy and momentum. We are squaring the momentum here, which means we're going to get rid of any direction here, dividing it by 2m. Those are scalars, so this gives us back a vector, and that'll all work out. And if you calculate your units out, this is a kilogram squared, meter squared per second squared. Divide that meter out, and you'll end up getting a joule as your unit here as well. Okay? I think that's pretty much everything for a little introduction to kinetic energy, or not kinetic energy, to momentum and impulse. And the next video will investigate, kind of ways to use them, or at least to use momentum for and conserving it for interactions of objects, in particular collisions, when objects collide and hit and bounce or stick together and things like that. So that's pretty much all for now.